Welcome to interference. We're going to use a few simulations to build up to this topic because it can be quite complicated. In this first simulation, we have a speaker which emits sound waves, and when we turn it on, we will see the peaks and troughs spreading from the speaker into the surroundings. So if we have a look at the particles, we can see them vibrating. We can see that the white areas are peaks or high pressure areas, and the black is the troughs or the low pressure areas. So we have a point source, and we have the waves spreading out from that source and arriving along this wall here. If we switch over to light, we can see that the light behaves in the same way. We have some control over this. We can change the frequency, so we can increase the wavelength, and you'll notice that the peaks and the troughs are more spread out. We can change to a high energy frequency where the distance between the peaks and the troughs is shorter. We have a shorter wavelength. Okay, here we have two sources of waves. We are back to sound, and if we have a look at these wave sources, they each give out a circular wavefront. So we've got this one up here, and we've got the one at the bottom which also gives out circular wavefronts. What we're interested in is the effect that we get when both of these are operating at the same time. So what's happening is that those circular wavefronts are now overlapping and interfering with each other. They are combining. They are adding together. The amplitudes are adding together, and we get this very distinctive pattern. I'm going to turn the frequency up so that this pattern is more distinct. And I'm going to pause it there, and we can see what's going on. So what's happening is that where you get these very, very strong light, dark, these are the peaks and the troughs. And in the center, we can see that they are very, very distinct. When these waveforms overlap, the peaks and the troughs, they get very, very high amplitude. But these zones in between, over here, this sort of grey area, that is an area of zero amplitude, where the peaks and the troughs have overlapped to cancel each other out. So you actually get zero amplitude along this line here. And if we put the screen up, so this is light with a screen, then you can see that in this area here, where the peaks and the troughs are constructively interfering to produce much higher amplitudes, we get a bright spot. And in this area here, where the peaks and the troughs are aligning so that they cancel each other out, we have destructive interference. We actually have a dark spot, an absence of light. If we change some of these properties, then we can change the separation of these bands. So let's take a measurement. It's a bit difficult because the bands are so wide to get an accurate measurement, but we'll do our best. So let's put this roughly in the center of that bright fringe and measure distance from that to the next bright fringe. So we've got this reading, and what we can do now is we can change the frequency. So if we change that to a lower frequency and watch the animation, then we will see those circular wavefronts overlapping, constructively interfering in the center, destructively interfering here and here, and those fringes are further apart. So if I put this in the center of the bright fringe here, you can see that this other cross is nowhere near the center of that fringe. So those fringes are further apart with a lower frequency. If we try with a higher frequency, then we get a different pattern. These fringes are much closer together, and compared with the green light, we can see that those fringes, here's the center of that one, and the green fringes, the center was over here. So this is much shorter. So the frequency has an impact on the separation between the fringes. Let's have a look at the amplitude. If we turn that down slightly and then wait for the effect to cascade through, we should see that the fringes become less bright, but the separation distance is still the same. And that's because it's the frequency of the light that's creating this effect. If we were to bring the screen closer to the light sources, then we would be sampling the fringes. Instead of being at this position, we'd be sampling the fringes over here. And that would cause the fringes to be in different positions. So the geometry also has an impact. Let's have a look at the separation between the wave sources. So for the purple, we've got the center of that fringe and the center of this fringe. So we have our distance there. Let's see what happens if we were to decrease the separation between the waves. So bring them a bit closer together. And it looks like the fringe separation has increased. And if we put them further apart, the fringe separation has decreased. So we're actually into the next fringe over by this point. So we're starting to see that there are lots of different variables, and each of them has an impact on the separation between the fringes. We've got the frequency of the light, or the wavelength. We've got the distance between the screen and the light sources, and the separation between the light sources. Let's now have a look at a famous experiment called Young's double slit experiment. So we have a light source over here, and this is a coherent light source. All of the light being emitted has the same frequency, and it is all moving as one. It is in phase. So all of the peaks are lined up, all of the troughs are lined up. This is a coherent light source. If we put a single slit in the way, then what happens is that that light diffracts through the slit. And if we look at what arrives at the other end of the simulation, what happens on the screen over here, we can see that there is a bright spot in the middle where the light is traveling the shortest distance and has the most energy. And over here, toward the top and toward the bottom, that light is more spread out when it arrives on the screen. The energy is more spread out and less intense. So we have a high intensity spot in the center, and then it gets darker towards the top and the bottom. If we change this single slit to a double slit, then essentially what we're doing is we have two sources of spherical waveforms, just like we had when we had two separate light sources. And we get an interference pattern, and we get these bands again. Thomas Young did this experiment in 1801 and was able to prove that light behaves like a wave, and that's because light diffracts and particles do not. You can only get this pattern on the screen if the light has diffracted through the gaps, interfered as it overlaps, and then arrived at the screen having constructively interfered at the bright spots and destructively interfered to create the dark spots. Let's have a look at some of the mathematics behind this. Thomas Young used his double slit experiment to prove that light behaves like a wave. He passed light through two slits, it overlapped, and it interfered creating an interference pattern on the screen. Particles cannot diffract. Particles cannot interfere and create a diffraction pattern. Only waves can do that. Therefore, light does behave like a wave. Thomas Young proved in 1801 that light definitely behaves like a wave, and at the time everybody thought that was the end of the discussion, until of course the photoelectric effect threw doubt into that and we discovered wave-particle duality. But for now, we're looking at light being waves. If you recall the changes to the different variables that we looked at in the simulations, you will remember that we were studying the fringe spacing. And that is given as W, or the width. So if we have a bright spot in the center here, and the next fringe is over here and over here, then the distance between the center of those fringes is given as W. We have the wavelength of the light as well. We were also looking at the distance between the slits and the screen. And we were looking at the separation of the slits as well. Okay, and when we changed these variables, we observed changes in the fringe spacing. We noticed that if you increase the wavelength, then the fringe spacing increases. So we have a proportional relationship. We observed that if you decrease the distance and you bring the screen closer, then you're going to be sampling those bright fringes before they were able to spread out so much. So if we think about those fringes as spreading out to hit the screen at those locations, then this fringe would be over here if you move the screen closer, and this fringe over here, which is spreading out in that way, would be here. And so suddenly the fringe separation is smaller than it was before. So if you decrease the distance between the slits and the screen, then you are decreasing the fringe spacing, a proportional relationship. If you decrease the separation between the slits and you bring them closer together, then you are increasing the fringe separation. And there we have an equation. This is the equation that you will need to use. And it can be deduced by observing the relationships between these variables and the fringe spacing, and then turning that into an equation. We're now going to look in more detail about the constructive and the deconstructive interference that leads to this interference pattern. So remember, if we have a peak and a trough and a peak and a trough, and that gets added to a trough and a peak and a trough and a peak, then this positive amplitude added with the negative amplitude will end up being 0. This negative added to the positive is 0, etc. So if you have waveforms that are 180 degrees out of phase, or pi radians out of phase, then you get nothing at all. You get a flat wavelength, and that would be a dark spot. So we see that when it's 180 degrees out of phase, which you get when you are half a wavelength out of phase. So these dark spots here and here as well, they occur when you are half a wavelength out of phase. If you have a wave with a peak and a trough and a peak and a trough, and you add that to a peak and a trough and a peak and a trough, then this peak and this peak added together make a larger peak. And this trough added to this trough makes a very deep trough indeed. Same again over here with this peak and this trough over here. So what happens is that the wave has a greater amplitude, and that would be a bright spot. So for example, here in the center. And you'll notice that the two waveforms that cause this constructive interference are in phase with each other. They are in phase, or they are 0 degrees out of phase. Sometimes people say 360 degrees out of phase. But the difference between their phases, the difference between the waveforms, is 0 wavelengths. They are exactly lined up. So when we get these bright spots in the center, the difference in the path taken from one slit compared with the path taken from the other slit, the difference in distance is going to be 0 wavelengths, or maybe 1 wavelength, because that would still make it in phase, or 2, or 3, or 4. Essentially, it's going to be an integer number of wavelengths out of phase. That number might be 1, 2, 3, 0. It's going to be arriving in phase. Let's have a look back at the simulation and see if we can identify this pattern. Okay, so here's our double slit experiment. I'm going to pause the simulation so that we can take the measurements. First thing to do, notice that the frequency slider here doesn't actually tell you what the frequency is. This little measuring tool over here is not measuring one wavelength, it's just giving you a handy indicator. So what I'm going to do first of all is work out what the wavelength is of this wave. I'm going to do it by putting one of the cross hatchings in the middle of this peak here, and then I'm going to measure as many as I possibly can so that my answer is as accurate as possible. So there's one wavelength, 2, I'm going to do it over 3 wavelengths, so peak to peak, and then to another peak, and then another peak. So that number divided by 1, 2, 3 gives us our wavelength of 657.8 nanometers. Doesn't really matter what the number is. I'm going to save it into the memory of my calculator so that I can now divide by that number whenever I want. What I'm interested in is how many wavelengths different is the journey from this slit over here to a bright spot compared with the journey taken from the light leaving the other slit. So what I would expect to see at bright spots is that the path difference, the difference in the distance travelled from each slit, is going to be a whole number of wavelengths at a bright spot and half a number of wavelengths at the dark spot. So let's have a look at that. So let's do this central bright spot first of all. So the path difference should be 0 because this bright spot is equidistant from these two slits. So let's just quickly test that out. And remember, of course, that this is an approximate answer only. So if I take that number and I calculate how many wavelengths that is by dividing by the number that we got previously, it tells me that it's 4 wavelengths. If I look at the distance from the other slit, this should be 4 wavelengths as well. And it is. So this bright spot here, this bright fringe, is equidistant from the two slits. The light from each of those slits is travelling the same distance to get to this bright spot, and that's why they're arriving in phase, because they're both travelling the same distance. They haven't had any distance to get out of phase. Whereas another location, for example down here, you'll notice that the distance travelled from the top slit is much, much further than the distance travelled from the bottom slit. But it's a bright spot, so I would expect the path difference to be a whole number of wavelengths. So let's try that out now. Am I lined up properly? I am. Okay, so there's the centre of the bright spot. How many wavelengths is that? 4 wavelengths. I would expect the number of wavelengths up here to be larger, and the difference between those numbers to be a whole number of wavelengths. So this is 5 wavelengths. So you'll notice that we've got 4 wavelengths distance coming from the lower slit, 5 coming from the top. The path difference is 1 wavelength. And because it's a whole number of wavelengths, they are arriving in phase, they are reinforcing each other, and you get that bright spot. We get the peaks adding together, the peaks are arriving with the other peaks, the troughs are arriving with the other troughs, and we're getting that increase in amplitude. We should not find that pattern at the dark spots. So let's look at a dark spot now. Let's look at this one over here. So how many wavelengths does it take to travel from the top slit to this dark spot? It is just under 4.5. So just under 4.5 wavelengths, and the other just under 4 wavelengths. So the difference between the distance travelled from the light coming from the top to that dark spot and the light travelling from the bottom slit to this dark spot, the difference in the distance travelled is half a wavelength. We should find the same pattern happening with this other dark spot, so let's quickly check. It's just over 4 wavelengths. It's just under 4 wavelengths, so it's about a half a wavelength difference. Let's have a look at those numbers written down. So very briefly, we've got our 2 slits, and the light coming from each of those slits is travelling a different distance to arrive at different parts of the screen. So for the bright spot in the centre, the light travelling from those slits is travelling the same distance, and that turned out to be 4 wavelengths. They were both arriving doing the same thing at the same time. They were going 4 wavelengths, peak, trough, 1, 2, 3, and they were both arriving doing the same thing, 2, 3, 4. They were both arriving doing the same thing at the same time. They were arriving in phase. The bright spot down here, the light from this slit was travelling a much further distance compared with the one down here, but they were still arriving doing the same thing at the same time. And the reason for that is because they were both travelling a distance that meant that they were in phase when they arrived. The difference in their paths, the path difference, was 5, take away 4 wavelengths, 1 whole wavelength. So they were arriving 1 whole wavelength out of phase, but that's still in phase. They were doing the same thing at the same time, peaks with peaks, troughs with troughs. Let's compare that to the dark spots. So the light arriving at this dark spot is travelling a slightly shorter distance than the light travelling from up here, and the difference in the distance of that path was half a wavelength. So when we did this measurement here, it was just under 4 wavelengths. It was 3 3/4 wavelengths, and this path was just over 4 wavelengths. It was 4 1/4, and the difference between those two numbers is a half a wavelength. So they were arriving half a wavelength out of phase because this one at the top had travelled further. The path difference was half a wavelength, so they were arriving out of phase doing the opposite thing. So if the one at the top is arriving with a peak, then the one at the bottom from the bottom slit was arriving with the trough. And that's what caused the light to cancel itself out and create a dark spot. The other dark spot was doing something similar, except this time the light from the lower slit was travelling the further distance. It was travelling just over 4 wavelengths. It was 4 1/4, and this one was travelling 3 3/4 wavelengths. Again, the difference between those two values is half a wavelength. A quick note about lasers, because most often we do these practicals using lasers. Lasers are very, very high energy light sources. It's very important that you never point them at your eye or shine them in a direction where there are people. You need to take into account reflections as well. If a laser reflects off a surface, it can enter somebody's eye, so please be very careful about the way that you are designing your experiment. You do not need to know how lasers work or how the light is produced in order to get a good grade in your A-level. If you're interested in that, then by all means do the research, but it's not something that you need to understand as part of AQA A-level.